Well, it's great to be in Berlin, our beautiful capital of Germany. Germany is doing well. I mean, thanks to the prosperity generated by the companies, really, some of which are more than 100 years old, founded by the great German industrialists, right? We are the economic motor of Europe. I mean, arguably, the whole thing started during the Industrial Revolution, when the quality of manufacturing here started to surpass what was available elsewhere, and made in Germany became a badge of honor. Who knows here what made in Germany originally was intended for? Okay, a few folks. So for those of you who don't know that, it was actually intended to be a badge of shame, for shoddy quality. It's not made in Britain, so it can't be good. Britain obviously started the Industrial Revolution. So need to get the clicker. So, well, Industrial Revolution. I mean, every once in a while, humanity turns a new page, and that surely happened in the late 1800s. When manufacturing became mechanicized, and the age of mass production began. So I believe that we are at such a historical turning point again, and we better watch out. We better be ready to lead and drive this change, because there's absolutely no guarantee that those who drove the last change and came out on top, us, will do so again this time. So, I mean, we've all heard the Industry 4.0 term, right? And unfortunately, different people mean different things when they talk about it. So I want to give a little bit of a broader perspective, so broad, in fact, that I will start right in the Stone Age. So please indulge me for a little bit. So it started all about 2.5 million years ago, really, when the first primitive humans started to use the first primitive tools. So this is me with my good friend Lucy. She wanted to come, but she has some kind of medical problem right now, so she'll stay in Addis Ababa. But, I mean, she looks great for her age. I mean, think of it. So Lucy and her team put us on track to building everything around us. All the physical aspects, but obviously all of human society. But progress at first was incredibly slow. I mean, think about how long it took us to invent the wheel. I'm not even talking about how long it took us to put wheels on our luggage. That's a very different story. So anyway, but at first we built everything by hand, basically like Lucy did, until about 150 years ago. If you think about it, if you look at an old building, chances are that every element of the building looks slightly different. Every stucco element, every staircase, every window is slightly different, right? Because essentially they were one-offs. The stonemasons who built this building here didn't care whether they built a little figurine that way or that way, the next day. It was all basically individual objects. But then, obviously, something changed. The Industrial Revolution happened. And ever since, we've been trying to build stuff from as many off-the-shelf parts as possible. We don't really want stuff that's different all of the time. It increases costs, it's not really effective. So mass production really was a breakthrough in the availability and affordability of objects. I mean, 200 years ago, everybody who had shoes had custom shoes. Unfortunately, a lot of folks didn't have shoes, so it was a big advantage when we could mass produce something like shoes. So ever since, we've been building stuff by the billions. But something happened there that also incurred a cost. So we had to generalize, we had to standardize. And today, if I want a custom thing, I choose the color of my car. That's about what I get. So also, if you think really about the manufacturing methods, they didn't change that much from Lucy's time. Obviously, I mean, we have improved techniques and technologies that help us, but we still basically start with a big block of material, and then we carve, we drill, we mill until we get the desired shape, and then we stick it to another part, and that builds our machinery. It's not that different from the way Lucy built, the first hammer. Obviously, much improved. We can be proud of what we did, but generally, it's very similar. So an industrial robot today is essentially a super fast stone chipper, very, very fast. But now we are entering a new era, and it will be mostly driven by additive manufacturing. So what is additive manufacturing all about? Why is that so special? Well, additive manufacturing works very similar to the way nature works. So how does nature work? So look at this tree. Isn't that amazing that this natural object, self-assembled, using the absolute minimum amount of energy and the absolute minimum amount of material to build the perfect tree for that specific location? I mean, isn't that crazy? No two trees are alike. Wouldn't it be cool if we could build something like that? So who is an engineer here? Okay, a few folks. So who's working for a company that builds physical objects? A few more even. Well, I hate to break it to you, but see that little cactus here? This meager little thing on your desk? It beats your most complex designs by, several orders of magnitude. This is 1 billion times more complex than anything in this room. I mean, isn't that kind of shameful? I mean, I'm just saying, 2 million years of human evolution and really? Okay, this is your competition. Really, 2 million years of human evolution and we are bet by a silkworm or a mushroom. Where's our dignity? Okay, anyway, so about 30 years ago, we invented additive manufacturing. It will help us catch up a little bit. So up until recently, 3D printing was really only used for prototyping or complex one-offs like prosthetics, very expensive. But increasingly, 3D printing is being used for the production of end-use parts. So parts that are actually make it into the final machine. And that is a big deal because now all of a sudden large factories are being established that have nothing in them but 3D printers for the manufacturing of objects that cannot be built any other way. And that's a really big deal because it's going to put us on the exponential track with this technology. Once large-scale additive manufacturing is out there, something that will happen that has happened previously in our technological history, quite recently, in fact. So I have to admit, I lied when I said the potted plant is more complex than anything we humans have ever created. There are things we have built where we have maybe even surpassed what nature is capable of. So I live in Munich. Berlin is nice, but really, have you been to Munich? Okay, yeah, some people know what I'm talking about. Anyway, so one of my favorite museums in Munich is the Deutsches Museum. It's actually one of my favorite ones in the world. And if you go all the way upstairs, there's a fantastic exhibition. I can recommend that you go there, where we see some of the most amazing mechanical marvels that we humans have ever created. So look at this mechanical calculator here. You can't help but be in awe at the complexity of this object, considering the age. Really cool stuff. Lots of part, really a lot of effort went into these calculators. And this went on for a couple of centuries until people like Charles Babbage were able to design objects that could not actually be built at that time. So this here was built more than 100 years after his death, in the 1980s. Difference engine. So we all know what a huge deal it was when Konrad Zuse developed the first modern computer. I mean, modern, right? I mean, he stood on the shoulders of giants like Charles Babbage and Lady Ada Lovelace, the first computer programmer. Who here knew that the first computer programmer was a woman? Okay, all the women, yeah, okay. Great, tell your daughters, please. Anyway, so, but if you look at the machines, I mean, there were still machines there where you had to have many moving parts, and they were wired together, and it was really, really complex to assemble these things and produce these things. And so there's no wonder, really, that Thomas Watson, famous IBM founder, said there's probably a market of about 5 computers in the world, right? He said that in 1943. But then the transistor was invented, and then finally the integrated circuit, and that changed everything. So before I continue, I want to highlight how similar the situation is of general production with, compared to the early computers. There's, a lot of moving parts. Yeah, we can build complex machines. We can build cars, we can build spacecraft, we can build, anything. We can be very proud of what we can build, but it involves a lot of manual labor, a lot of parts need to be assembled, it's quite complicated, and there's a natural limit to the complexity of the things that we can really do. So, just as with the early computing machines, it required a lot of skill to build these things. And this barrier simply stopped us from going further. So let's look at what happened with the integrated circuit. So at first, the design of the circuit became virtual. I mean, instead of wiring transistors together, we moved them around on the screen, and connected them virtually, and then it was printed on a wafer. And then, of course, as software works, right, people said, oh, we don't actually have to move every transistor. Let's put up functional blocks like a memory and the processing unit and all of the stuff, and then you wired the functional blocks together. And that increased the output of the designers tremendously, right? But the process was still the same. You printed it on a wafer and off it went. So the bottleneck was really the design. But today, it actually changed dramatically. So today, we don't actually wire transistors together, not even virtually on a screen. We describe in fairly abstract terms what we want from a microprocessor, and then the computer actually designs the chip for us with almost no human intervention. And that is what enabled Moore's law. That put us on the exponential track with computer technology. Because now the designers could work on really, really, really abstract terms. So essentially, we moved from a model where it still was a lot of manual work to a model where basically we are only limited by imaginations. So think of Charles Babbage. I mean, his masterpiece was the connection, the difference engine. And the difference engine took him 25 years just to design it, and then there was no way for him to build it. Today, any high school kid can really whip up a design 1 billion times more complex and then print it in a fab in China. So it's kind of a big deal, right? So this is what enabled Moore's law. This is why we're now talking about computer vision, self-driving cars, artificial intelligence, and whether you and I, with our wet, messy brains, gray matter, whether we are still going to be the smartest people in this room a couple of years from So, I think this is now happening with general manufacturing, now that 3D printing has come of age. We are at a similar turning point. Manufacturing will also start operating under Moore's law. So why is this happening now? Why isn't this happening? I mean, 3D printing was really invented 30 years ago. Why is this a big deal now? Why not like 10 years ago? Why not in 5 years? I mean, first of all, 3D printers have really matured to the point where we can work with almost any relevant material. You know, metals, concrete, you know, polymers, obviously, living cells, very interesting topic. The speed has increased, the reproducibility of the results have increased, the quality has increased. This is all great. But I would argue that something else has happened as well. So increasingly, people become familiar with the capabilities of the printer. And I would think this is the most important aspect of it. Engineers are starting to imagine mechanisms that were unimaginable before, because you could not actually work with that. You know, self-enclosed materials, you know, assemblies where you don't actually assemble anything. You know, self-enclosed parts with moving things inside. I mean, look at this stuff here. This is a 3D sculpture made by my friend Andy Lomas in London. And right now he's selling them as paper prints, you know, as fine art. And there's no way to actually build a physical model. It's about this size. We're currently trying to help him to print this. I mean, it's probably a little bit beyond the capabilities of today's printers, but we'll get there. So for the engineers in this room, think of what you could actually do with these capabilities. Because a 3D printer doesn't care how complex an object is. A 3D printer doesn't really care whether you print something round or straight, or flat or ornamental. The cost of an object is essentially determined by the type and the amount of material that you use, and not much else. Think of what a game changer this actually is in the way you think about stuff. So, and it is for these parts that companies are investing hundreds of millions into factories that have nothing but 3D printers in them, factories of the future. Now, since these factories exist now, something interesting is going to happen. The engineers are going to feel empowered to actually use the capabilities of the printers, which will increase, you know, the utilization of the printers, which will then in turn increase the demand for more printers from established players and startup, which will then again, you know, give the designers more stuff to work with, and you know, you're generating a virtuous cycle. So it will start to accelerate. So as the adoption increases, people will go onto a completely different trajectory with their innovation. Think of Moore's law and what it did for computer business models. All of a sudden, you could kind of rely on that every 1 or 2 years, processing power would double, prices would fall. Think of what would happen if something like that occurred in general manufacturing. So we've seen this stuff a couple of times, right? And I don't actually like it. I think this leaves out the most interesting part of an exponential curve. So I actually had to sit down with Excel and create a new exponential curve. So that is a true exponential curve, right? So, I mean, this is the early computers, and this is where we are today. And, you know, just for reference, this has been going on for a long time. I mean, Lucy is over here, right? You are here, carrying a relatively big computer. So one of the interesting aspects, by the way, of an exponential curve is, if I take any segment of the exponential curve and magnify it, I get the same thing again. Think of it as you look at this part of the curve. So my question to you, when you look at your design challenges, when you look at your production challenges, are you taking this stuff into account? Are you thinking about producing objects that may not be quite possible to produce today, but maybe next year or the year after? Are you thinking about production economics in a different way? Because, they are kind of the laws of physics right now. But what if things automatically get cheaper every year? What if complexity didn't matter anymore? That's a big deal. So are you investing significant resources in the technologies that are relevant to you? Are you doing that today? Are you giving your designers kind of a playground where they can experiment with new ideas, with an open outcome? Are you doing that? Because if you're not, you may set yourself up to become irrelevant. And that's the danger that I talked about earlier. So I know today this requires a big leap of faith, but just imagine, leaping involves jumping, and if you jump to the right spot, you may be the next leader in your field, or stay the leader in your field. So what are we talking about? What capabilities are there and will be there that you can take advantage of, right? So usually when people think about industrial 3D printing, they think of aerospace space parts that are shaped organically. This is a great example. This is Airbus AppWorks group that they created this 3D printed motorcycle. You can lift it with one hand. It's extremely light. So this is great. This is moving from a vacuum tube to a transistor. Nothing wrong with that. That's great. But additive manufacturing has so much more stuff in store for us. So actually, I brought some props with me. So look at this seashell. I brought one with me. So here it is. I brought something else with me. So what does the seashell consist out of? It's calcium carbonate, also known as chalk. So just for comparison, I brought a little piece of chalk here. So how come this thing is so incredibly solid and this is not? So it is because as this shell grew, it used tiny pieces of chalk and glued them into place with protein glue. So 99.9% of this seashell is chalk. And 0.1% is protein glue. And because it glued the chalk into place in microscopic patterns that makes it extremely stable, it kind of generated this metamaterial that had very, very little to do with the original source materials. So try to break this. I won't break it. My kids will get angry at me, but anyway. So this is stuff we can do today with 3D printers, right? We can use metals, multiple metals, and mix them as we print. We can use polymers and change the polymer quality as we print on the microscopic level. And that enables us to create amazing stuff that has never been possible before. And we can use all the materials that we humans discovered in the past couple of thousand years, including concrete, metals, polymers, carbon nanotube, you name it. Nature actually doesn't have these kinds of materials. Nature doesn't use metals, for example. But with the few materials that nature uses, it generates all the amazing natural things around us. So imagine what we humans can do now that we've unlocked this capability. Imagine changing the local composition of a rocket nozzle from copper to titanium according to the heat distribution. And we're obviously not limited to static objects. You can print moving parts. You can place electronics as we print. and wire them together with 3D printers' wires. We can do that today. Yeah, we are maybe a couple of years away from printing electric motors and actuators. Think of what this will mean for your products. Because essentially, you can add intelligence to it. You can, Pascal talked about, why is my toaster getting intelligent? Yeah, because it doesn't cost anything anymore. So this is kind of this whole thing on a completely different scale. It doesn't even cost anything to place the chip because it's going to be placed automatically. So you can add intelligence, you can add lights, you can add displays, you can add moving parts, essentially for free. Again, the only thing that matters is how much money costs the source material and how much am I using. So are you taking this stuff into account as you build stuff, as you plan for the future of your companies? Today, complexity is expensive. Today, complexity always means more manual work and more spending of resources. So we try to get by with less. Today, customization and individualization is basically for the rich and famous. But it's no longer the case in this new world, in this new paradigm. Like the stonemasons who build our old buildings, a 3D printer doesn't care whether it prints the same object every time it goes to work or a completely different one. So you can individualize objects as you work. And once on the software side, we cross over to the point where designers don't have to sweat over every little detail. Because if you think about it, right now, a CAD/CAM designer does exactly what a carpenter does. She starts with a big block of material and then drills holes into it, and just virtually on a screen. So the designer has to spend work on every little detail of the construction. So we have to move on the software side to a model where, like with chip design, we describe in abstract terms what we want, and then the computer generates most of the stuff for us. So this is what I'm working on. And once we get there, we will start operating under this new model for real. And we must really, folks, because there's another aspect in which we need to mimic nature. I mean, despite our great attempts at reducing the ecological footprint of production, we are still very wasteful when we are compared to nature as a builder. In this new paradigm, we can actually spend less energy, produce less waste, and use this really renewable resource that we've come to rely on ever since Lucy's time, which is human imagination. So, whenever we invented new tools, humanity took a giant leap forward. So let's use these tools. Let's use our imagination, and let's make Lucy proud. Thank you very much. Do we have some minutes for?
A couple of minutes for questions, yes.
Okay, so we have a couple of minutes for questions. Okay, gentlemen over here, do we have a mic? Here, do we have a mic? Any mic runners here? Here.
Thank you. As Moore's law in computing is ending, can you talk a bit about atomic computing?
Well, yeah, it's a good question. First of all, I would challenge the question whether Moore's law is really ending, because now with quantum computing, we're like getting on a completely different trajectory with Moore's law. But yeah, I mean, obviously, you saw Charles Babbage difference engine, and all the mechanical parts. Now we are moving to a point where we can do similar things on the atomic level, right? And so, yeah, I mean, there's some really interesting developments in that regard, that you're combining nanotechnology with traditional 3D printing, and you're putting some of the computing actually, down in that level. Yeah. So, any other questions?
Questions?
No more questions?
Okay.
Where's the lady that had a question yesterday every time she... Okay. those were great questions.
Thank you.
So we have a deep dive session where hopefully some people will come up with some more questions. I just want to end with one small thing that, here in Germany, we're sometimes a little bit cautious when it comes to the future. And I think this is something that is changing right now. We have a lot of great startups. But I just wanted to read you a message I got the other day during my workday. So I get this nice message here from an entrepreneur. I'm in Munich having lunch with Jeff, who says we should meet. I'm looking to 3D print a moon base. This is my daily work. I love it. Thank you very much.
Thank you, Lin.